Gaze into the heart of absolute darkness, where even light itself vanishes without a trace. What you're witnessing isn't some science fiction fantasy. It's a real supermassive black hole, containing the mass of billions of suns compressed into a single point of infinite density. That glowing ring of incandescent gas swirling at nearly the speed of light, that's the accretion disk, the final farewell of matter about to cross the event horizon and disappear from our universe forever. For decades, we've pictured black holes as cosmic vacuum cleaners, terrifying monsters that simply devour everything in their path. But what if I told you that black holes are actually the universe's most mysterious and powerful engines, architects of galaxies, creators of elements, and perhaps even the key to understanding reality itself? Today, we're embarking on an extraordinary journey to explore 30 incredible facts about the largest black holes in existence, cosmic giants so immense they defy comprehension. We'll venture from the relatively nearby supermassive black hole at the center of our own Milky Way to the incomprehensibly vast behemoths lurking in distant quasars, each fact revealing another layer of their profound mystery. These aren't just astronomical curiosities, they're fundamental forces that shape the cosmos around us, governing the motion of stars, the formation of galaxies, and potentially holding secrets about the very nature of space and time. Imagine standing at the edge of one of these gravitational monsters, witnessing the laws of physics unravel before your eyes. Over the next 30 revelations, you'll discover how black holes create the brightest objects in the universe, how they might contain hidden dimensions, and how they ultimately hold the fate of entire galaxies in their invisible grasp. This exploration will challenge everything you thought you knew about these cosmic phenomena and leave you with a profound appreciation for the incredible universe we inhabit. So prepare to have your perspective completely transformed as we dive deep into the fascinating world of the universe's largest black holes. Our journey begins with a staggering discovery that reshaped our entire understanding of the cosmos. For the longest time, black holes were considered theoretical oddities or rare cosmic accidents, but we now know that these giants are not the exception, they are the rule. The very first mind-bending fact is this: nearly every large galaxy in the observable universe, including our beloved Milky Way, has a supermassive black hole sitting at its very heart. Think of them not as silent monsters hiding in the dark, but as the gravitational anchors of their galactic cities, the invisible engines around which billions of stars slowly dance. Our own cosmic home is no exception. At the center of the Milky Way, roughly 26,000 light-years from Earth, lies a celestial titan named Sagittarius, a star. This supermassive black hole is a behemoth containing the equivalent mass of 4 million suns, all crushed into a region of space no larger than our solar system. For decades, its presence was only inferred by the frantic, whirling dance of stars caught in its immense gravitational pull, stars being slingshotted around at millions of miles per hour. Then, in a monumental scientific achievement, the Event Horizon Telescope collaboration delivered the first ever direct image of its shadow, confirming beyond any doubt the existence of this colossal object. But their role extends far beyond simply being present. These central black holes are fundamental architects, actively shaping the evolution and structure of their host galaxies. Their immense gravity dictates the motion of stars in the galactic core, and their activity cycles periods of intense feeding and explosive outbursts can either trigger or quench the birth of new stars across vast distances. They act as a form of cosmic regulation, preventing galaxies from growing too large and stabilizing their very form. It's a profound cosmic partnership. The galaxy feeds the black hole, and the black hole, in return, governs the galaxy's destiny. This symbiotic relationship suggests that to understand the life story of any galaxy, we must first listen to the silent, gravitational heartbeat of the giant at its center. And if our own galactic center seems immense, prepare to have your sense of scale completely rewritten. While Sagittarius, a star, anchors our Milky Way, it is a mere pebble compared to the true leviathans that roam the cosmic deep. This brings us to our second astonishing fact. The largest known black hole in our universe is a colossus of almost incomprehensible proportions. Known to astronomers as Ton 618, this gravitational titan doesn't just break records, it shatters our very understanding of what is possible. Residing in the distant constellation Canes Venatici, over 10 billion light-years from Earth, Ton 618 is a supermassive black hole of such staggering immensity that numbers alone fail to capture its true nature. To put it in perspective, this cosmic beast contains the mass of 66 billion suns. Let that sink in for a moment. Every star in our Milky Way galaxy, all 200 billion of them, amount to only a fraction of the mass contained within this single, unfathomable point in space. The sheer gravitational dominance of such an object is beyond human comprehension. Its physical size is equally staggering. The event horizon of Ton 618, the point of no return for light and matter, is not merely large, it is a gaping chasm in the fabric of spacetime. If we could place this black hole at the center of our solar system, its shadowy boundary would stretch outward in a sphere so vast it would completely engulf the orbit of Pluto and extend more than 10 times farther into the void. Every planet, every asteroid, every speck of dust in our familiar celestial neighborhood would be residing deep within its dark embrace, forever severed from the rest of the universe. Yet, for all its darkness, Ton 618 is also a beacon of unimaginable light. The matter spiraling toward its doom forms an accretion disk of such ferocious intensity that it shines with the luminosity of 140 trillion suns. To grasp that figure, consider that every star in every galaxy we can observe in the night sky with the naked eye combined would pale in comparison to the radiant fury of this single object. This makes the environment around Ton 618 one of the most violently energetic places in existence, a maelstrom of superheated plasma, intense radiation, and magnetic fields powerful enough to twist the very fabric of reality, proving that the largest black holes are not just voids of darkness, but the engines behind the universe's most brilliant lights. Now, the existence of such incomprehensible giants as Ton 618 naturally leads to a pressing question: how do black holes grow so impossibly large? The answer lies not in solitary feasting, but in a violent and majestic cosmic dance. The third incredible fact is that the very largest black holes in the universe achieve their staggering sizes primarily through a process of galactic collisions and mergers. They don't just consume gas and stars, they cannibalize each other, engaging in gravitational duels that end with the creation of a single, even more massive singularity. Picture two immense galaxies, each with its own supermassive black hole at the core, drifting through the void over billions of years. Drawn together by their mutual gravity, they begin a slow, inevitable collision course. As these galaxies finally merge, their central black holes are pulled toward the new galactic center. They start to orbit one another, locked in a tightening spiral that sends ripples through the fabric of spacetime itself. This dance can last for millions of years, a breathtaking celestial waltz between two of the most powerful objects in existence. The final act of this merger is one of the most energetic events in the cosmos. As the black holes draw within a critical distance, they lose orbital energy by violently ejecting stars and flinging huge streams of gas outward. But the main event is the emission of gravitational waves, ripples in spacetime predicted by Einstein. These waves carry away tremendous energy, causing the orbits to decay faster and faster until the two black holes plunge together in a cataclysmic union. In the final fraction of a second, they collide and merge, releasing a burst of gravitational wave energy so powerful that it briefly outshines the combined light of every star in the observable universe. The result of this colossal crash is a new black hole with a mass almost equal to the sum of its parents. However, the merger process itself is so violent that a portion of the combined mass is converted directly into energy and radiated away as gravitational waves, as described by Einstein's famous equation, E equals mc squared. This means the new entity is slightly less massive than the simple sum, but its gravitational influence is now dominant, sitting at the heart of a newly forged larger galaxy. This cycle of collision and consolidation repeats across cosmic time, explaining how the seeds of early black holes, perhaps formed from the first massive stars, could grow into the billion solar mass behemoths we observe in the ancient universe. It suggests that the largest black holes are not just inhabitants of galaxies, they are the products of their galaxy's most violent and formative history. To truly grasp the nature of these cosmic giants, we must venture to their most defining feature, the event horizon. This is the ultimate point of no return, the invisible boundary that marks the edge of the known universe. But contrary to what many believe, the event horizon isn't a solid, physical wall you could crash into. Instead, think of it as a one-way curtain in the fabric of spacetime itself, a region where the gravitational pull becomes so intense that the universe's ultimate speed limit, the speed of light, is no longer fast enough to escape. The physics behind this is both elegant and terrifying. Every object with mass has an escape velocity, the minimum speed something must achieve to break free from its gravitational grip. For Earth, that's about 11 kilometers per second, which is why our rockets can leave the planet. For a black hole, the escape velocity at the event horizon equals the speed of light. Since nothing can travel faster than light, nothing, not matter, not light, not even information itself, can ever cross back out. It's a permanent exit from our observable reality. What's truly fascinating is how the size of this boundary is determined. The radius of a black hole's event horizon, known as the Schwarzschild radius, scales in a perfectly straightforward way. It gets larger in direct proportion to the black hole's mass. Double the mass and you double the radius of the event horizon. This simple relationship means that the most massive black holes possess event horizons of almost unimaginable scale. Consider our own solar system for a moment, with the Sun at the center and Pluto orbiting at the edge of its domain, nearly 6 billion kilometers out. Now take a supermassive black hole like the one at the heart of the galaxy Messier 87, which was the first ever to be directly imaged. That black hole, though 6.5 billion times the mass of our Sun, has an event horizon with a radius of about 20 billion kilometers. That's large enough to comfortably contain the entire orbit of Pluto, but as we learned with TUN 618, that's still just a taste of the true titans. The event horizons of the largest known black holes are so vast they could swallow our entire solar system many times over, creating a sphere of darkness larger than some stellar nurseries. This direct link between mass and size means that by studying the shadow a black hole casts against its glowing accretion disk, astronomers can directly measure the immense mass of these invisible monsters, using the void itself as a cosmic scale. Now, while the event horizon defines the spatial boundary of a black hole, its gravitational influence warps something even more fundamental, the very flow of time itself. This brings us to our fifth astonishing fact, a concept that bends the mind as severely as spacetime itself. Near a supermassive black hole, time does not pass at a constant, universal rate. Instead, it stretches and slows in a phenomenon so extreme it could turn minutes into millennia. This isn't science fiction. It's a direct prediction of Einstein's theory of general relativity, and we see its fingerprints in the light from matter spiraling toward its doom. To grasp this, imagine a brave pair of astronauts on a mission to study a supermassive black hole like Sagittarius, a star. one astronaut, let's call her Alex, volunteers to descend dangerously close to the event horizon in a super-advanced probe, while her partner, Sam, remains in a safer, distant orbit. They agree to send a regular pulse of a light signal every second. From Sam's perspective, watching from afar, something bizarre happens. As Alex gets closer to the immense gravitational well, the pulses don't just get redshifted stretched to longer, redder wavelengths, they also arrive further and further apart. What Alex experiences as a 1-second interval is measured as hours, then years, then centuries by Sam. If Alex were to hover just above the event horizon from Sam's viewpoint, her time would appear to grind to a near halt, her image frozen forever at the precipice. For Alex, however, her own clock would seem to tick perfectly normally. 1 minute would feel like 1 minute. The incredible difference in experienced time is a real physical effect. This mind-bending occurrence, called gravitational time dilation, happens because a massive object like a black hole curves the spacetime around it. Think of spacetime not as a static stage, but as a flexible rubber sheet. A black hole creates such an incredibly deep indentation in this sheet that time itself is forced to flow slower near the bottom of the gravitational well compared to the flat regions far away. The stronger the gravity, the more pronounced the effect. For smaller black holes, where the gravity changes drastically over a short distance, this tidal force would be lethal long before time dilation became significant. But for a supermassive black hole, with its incredibly vast event horizon and more gradual gravitational gradient, an astronaut could, in theory, cross the event horizon without immediately being torn apart by tidal forces, experiencing these extreme time warps firsthand. We don't need to send astronauts to observe this, however. Astronomers can actually detect the signatures of time dilation when they watch matter fall into these giants. As superheated gas from the accretion disk spirals inward, the light it emits is not only redshifted, but its fluctuations, the flickering and brightening, appear to slow down from our distant perspective. We are, in effect, watching the final moments of that matter play out in extreme slow motion, a direct observational confirmation of Einstein's brilliant theory. This profound distortion means that if we could witness a star being torn apart by a supermassive black hole, the entire event, which might take hours from the star's frame of reference, could appear to be stretched out over years or even centuries from our safe vantage point here on Earth. The black hole doesn't just trap matter and light, it ensnares time itself, creating a cosmic arena where the laws of physics as we know them are pushed to their absolute limit. But if we think falling into a black hole means being consumed by absolute darkness, the universe holds a spectacular contradiction in store. The sixth fact is one of the most dazzling in all of astronomy. These gravitational giants are responsible for creating the brightest, most persistently luminous objects in the entire cosmos. They are the engines behind quasars, beacons so intensely brilliant that they can outshine the combined light of every star in thousands of galaxies, all emanating from a region of space no larger than our own solar system. The term quasar is short for quasi-stellar radio source, a name given because when first discovered, these points of light looked like stars but emitted bizarre amounts of energy, especially in radio waves. We now know they are not stars at all. A quasar is in fact the intensely energetic core of a distant galaxy, and its incredible power source is a supermassive black hole in a state of extreme gluttony. This isn't a dormant monster, but a voracious beast feasting upon a vast reservoir of gas, dust, and even entire stars that have ventured too close. The process of generating this unimaginable light begins in the black hole's accretion disk. As immense clouds of material are pulled in by gravity, they don't fall straight in. Instead, they form a flattened, spiraling disk of superheated plasma, much like water circling a drain. The friction within this churning maelstrom, combined with the incredible gravitational forces at play, heats the matter to temperatures of millions of degrees. At these extreme energies, the matter doesn't just glow. It emits a blinding torrent of radiation across the entire electromagnetic spectrum, from low-energy radio waves to high-energy X-rays and gamma rays. To truly comprehend the scale of this energy output, consider the numbers. A typical quasar can radiate 1,000 times more energy than our entire Milky Way galaxy, which contains over 200 billion stars. All of that staggering luminosity is generated in an area that is, on the cosmic scale, astonishingly compact. The entire brilliant engine, from the black hole to the outer edge of its glowing disk, is often smaller than the distance from our Sun to Pluto. This means a single object, not much bigger than our solar system, can produce more light than a vast island of stars hundreds of thousands of light years across. It is the most efficient and powerful engine for converting matter into energy in the known universe, dwarfing the output of nuclear fusion in stars by orders of magnitude. The light from these cosmic lighthouses is so powerful that they serve as beacons visible across the vast expanse of the universe. The most distant quasars we observe are seen as they were when the universe was less than 1 billion years old, their light having traveled for over 13 billion years to reach our telescopes. By studying them, we are essentially looking back in time to the early, violent epochs of cosmic history, when supermassive black holes were actively growing and shaping the fledgling galaxies around them. Their incredible brightness cuts through the fog of time and distance, allowing us to study the conditions of the ancient universe in exquisite detail, all thanks to the awesome power unleashed by matter in its final, glorious moments before vanishing into the dark. But the gravitational pull and dazzling light aren't the only incredible forces at work around these cosmic giants. These monsters don't just sit idly in space. Many of them are in a state of furious rotation, spinning at velocities that defy belief. The seventh astonishing fact is that black holes can rotate, and the supermassive ones often spin at speeds approaching the ultimate cosmic speed limit, the speed of light itself. This isn't a gentle rotation. It's a violent whirlpool in the fabric of spacetime that warps the very universe around it in ways that are both strange and profound. This spin is a form of angular momentum, a property it inherits from all the matter that has ever fallen into it. Just as a figure skater spins faster when they pull their arms in, a black hole's rotation accelerates as it consumes stars, gas, and even other black holes that carry their own momentum. The result is a singularity that isn't just a point but a ring, spinning so rapidly that it drags the very fabric of spacetime along with it. We measure this spin on a scale from 0 for a stationary black hole to 1, which represents the maximum theoretical spin where the rotational velocity at the event horizon reaches the speed of light. The implications of this spin are where the true magic of physics reveals itself. A rotating black hole doesn't just create a gravitational well, it creates a cosmic whirlpool. This phenomenon, predicted by mathematicians Roy Kerr and called frame dragging, means that the immense spinning mass literally pulls the surrounding spacetime into a vortex around it. Imagine stirring a cup of coffee with a spoon. The liquid is dragged around by the motion. In the case of a spinning black hole, the liquid is the fabric of reality itself. Space and time are forced to circulate around the black hole. This effect is so powerful that close to the event horizon, it becomes impossible for any object to remain stationary. You would be caught in the current of spinning space-time, forced to move around the black hole no matter how powerful your engines, as if you were caught in a relentless cosmic river. This swirling spacetime creates a region outside the event horizon known as the ergosphere, an oval-shaped zone of pure energy and twisted physics. Within the ergosphere, the frame dragging is so intense that not even light can move against the rotation. Everything is compelled to move in the direction of the black hole's spin. This bizarre region is where the laws of physics allow for possibilities that sound like science fiction. Because spacetime itself is being dragged around at incredible speeds, The rotational energy of the black hole is stored there, just waiting to be tapped. Theoretical models suggest that if a particle were to enter the ergosphere and split in two, with one part falling into the black hole and the other escaping, the escaping fragment could actually steal some of the black hole's rotational energy and fly away with more energy than it entered with. This process, known as the Penrose process, is a hypothetical way to extract energy from a black hole itself, turning it into the ultimate cosmic battery. The spin of a supermassive black hole also has dramatic consequences for its most visible feature, the jet. For the black holes that power quasars and active galactic nuclei, their rotation, combined with incredibly powerful magnetic fields generated by the churning accretion disk, acts like a colossal slingshot. These magnetic fields become twisted into tight helices by the spinning black hole, channeling and accelerating ionized matter from the accretion disk outward along the rotational axis. This creates those spectacular, narrow jets of plasma that can shoot out for thousands of light years at nearly the speed of light. The faster the black hole spins, the more energy it can inject into these jets, which can punch through entire galaxies, influencing star formation rates and shaping the cosmic environment on a monumental scale. So a black hole's spin is far from a trivial detail. It is a fundamental property that dictates how it interacts with its entire galactic neighborhood, transforming it from a passive vacuum into an active and powerful architect of the cosmos. While the theoretical groundwork for supermassive black holes was laid by geniuses like Einstein and Schwarzschild, and while their presence was hinted at by the frantic motions of stars at our own galactic center, it took a telescope free from the distorting shimmer of Earth's atmosphere to deliver the undeniable visual proof. The eighth pivotal fact in our journey is that the Hubble Space Telescope didn't just observe these cosmic giants. It fundamentally revolutionized our understanding of their role in the cosmos, transforming them from speculative monsters into confirmed architects of nearly every galaxy we see. Before Hubble's sharp eye was turned to the heavens, the idea that a supermassive black hole lurked at the center of every large galaxy was a compelling hypothesis, but it lacked the concrete evidence to become established fact. Ground-based telescopes, hampered by atmospheric turbulence, struggled to resolve the fine details at the hearts of distant galaxies. Hubble, orbiting high above this blurring effect, provided a crystal-clear window into the universe. Its unparalleled resolution allowed astronomers to do something astonishing, not just infer the presence of these invisible objects, but literally watch stars dance around them. The strategy was as brilliant as it was simple. By focusing on the dense cores of nearby galaxies, Hubble was able to track the precise orbits of individual stars over periods of years. Just as you can calculate the mass of the Sun by measuring how fast Earth orbits it, astronomers could use the velocity and distance of these stars to calculate the mass of the object they were whirling around. Time and again, the results were staggering. These stars were moving at incredible speeds, thousands of kilometers per second, around a seemingly empty point in space. The only explanation for such violent motion was the gravitational grip of an incredibly massive, incredibly compact object. A supermassive black hole was the only possible answer. One of Hubble's most famous and conclusive campaigns focused on the giant elliptical galaxy M87, home to the first black hole ever imaged. For years, Hubble meticulously mapped the motions of stars and the ferocious rotation of its gaseous accretion disk. The data revealed an irrefutable truth. At the galaxy's heart lay a dark beast weighing in at a phenomenal 6.5 billion times the mass of our Sun. This wasn't an isolated case. Hubble's surveys systematically revealed that these gravitational anchors were not rare cosmic anomalies, they were universal. Nearly every galaxy, examined from stately spirals to vast ellipticals, harbored a central supermassive black hole. This discovery established a profound and fundamental link between a galaxy and its central black hole, suggesting that the evolution of one was inextricably tied to the other. Perhaps one of Hubble's most surprising contributions was the revelation of a startling correlation. The telescope's data showed that the mass of a galaxy's central black hole is directly proportional to the mass of its surrounding bulge of stars. The larger the stellar bulge, the larger the black hole. This tight relationship was a cosmic clue of the highest order. It told us that black holes are not passive residents, they are active participants in the life of a galaxy. Their growth and activity must be intimately connected to the formation of stars, through processes like the colossal jets that can heat gas and suppress star formation, or the gravitational stirring that can trigger it. By providing this clear, observational evidence, the Hubble Space Telescope did more than just discover black holes. It unveiled the deep, symbiotic relationship between the visible galaxy of stars and the invisible engine at its heart, forever changing our perspective on how the universe builds its largest structures. For all their fearsome reputation, one of the most persistent myths about black holes is also the most misleading. The idea that they act like cosmic vacuum cleaners, actively sucking in everything from distant stars to stray light across the universe. This ninth fact is crucial to setting the record straight. Black holes do not suck, they simply gravitate. Their immense power comes from the same fundamental force that holds you to the ground right now and keeps the Earth in orbit around the Sun, gravity. A supermassive black hole exerts a gravitational pull no different in nature from that of any other object with mass. It's just concentrated into an almost unimaginably dense package. To understand why this distinction is so important, let's perform a simple thought experiment. Imagine our Sun, the gentle giant that sustains life on our planet. Now, what would happen if we could, in an instant, magically compress the entire Sun down into a black hole without changing its total mass? The result might surprise you. Earth and all the other planets would not be instantly devoured. Their orbits would remain completely unchanged. They would continue to circle that point of absolute darkness exactly as they did before, because the gravitational influence at those distances depends solely on the object's mass and distance, not on its size or density. The force that holds our solar system together would be identical. The only thing that would vanish is the light and warmth we depend on. This perfectly illustrates that a black hole's gravitational grip is powerful, not because it's a supernatural vacuum, but simply because it packs an enormous amount of mass into a vanishingly small point. This principle extends directly to their behavior within galaxies. Stars safely orbit the supermassive black hole at the center of the Milky Way, just as planets orbit a star. Their stability depends on maintaining a safe distance and a sufficient orbital velocity. The danger zone isn't some vast region of space, it's an extremely close proximity to the event horizon. An object can orbit a black hole perfectly stably for billions of years, so long as it doesn't experience friction or a collision that causes it to lose orbital energy and spiral inward. The fate of matter that gets too close isn't that it gets sucked in, it's that it can no longer maintain a stable path. Once matter crosses inside the innermost stable circular orbit, a region where no stable circular path exists, it's doomed to follow a rapidly decaying spiral directly into the black hole's maw. It's less like being pulled by a vacuum and more like slipping over the edge of a waterfall after fighting a powerful current. The transition is sudden and irreversible. This correction isn't just a matter of scientific semantics. It completely changes how we view these cosmic giants. They are not relentless, all-consuming monsters roaming the galaxy. They are gravitational anchors around which the intricate dance of stars and gas unfolds. Their influence is vast but orderly, governed by the same predictable laws of physics that govern the orbit of the Moon around Earth. A star that remains a healthy distance away can circle a supermassive black hole for the entire lifespan of the universe, utterly unconsumed. This more accurate picture reveals a universe that is not randomly dangerous, but one governed by elegant and understandable rules, even in the most extreme environments imaginable. This intricate cosmic partnership, often called co-evolution, reveals that the largest black holes are far more than just inhabitants of their galaxies. They are fundamental regulators of galactic destiny. The key to this profound connection lies in a series of feedback mechanisms, powerful processes where the energy unleashed by a feeding black hole directly influences the gas from which future stars are born. Imagine a galaxy as a vast stellar nursery filled with immense clouds of cold hydrogen gas, the raw material for new stars. Left alone, this gas would gradually collapse under its own gravity, igniting into new suns. The supermassive black hole at the center acts as a cosmic thermostat, capable of both turning the heat up in this nursery to trigger a baby boom of stars, or blowing the gas away entirely to shut down star formation for eons. One of the most dramatic ways a black hole can promote star formation is through the immense shock waves generated by its own explosive outbursts. When a black hole goes through a period of intense feeding, it doesn't just create a quasar, it can also trigger colossal outflows of energy. These aren't the narrow jets, but wider, slower-moving winds and bubbles of hot gas that expand outward through the galactic center. As these enormous shockwaves plow into surrounding cold gas clouds, they compress them. This sudden compression can be the final push that overcomes the cloud's internal pressure, causing it to collapse and fragment into dense cores that ignite as new stars. In this scenario, the black hole's furious activity acts as a cosmic trigger, initiating a wave of star formation that propagates outward from the galactic core, essentially using its own explosive energy to build the very galaxy it resides in. Conversely, these same black holes possess an even more powerful ability to quench or shut down star formation entirely. This is the dominant form of feedback in the largest galaxies. The process begins when the energetic radiation and powerful jets from the active black hole pour immense energy into the surrounding galactic environment. This energy heats the vast reservoirs of cold hydrogen gas, preventing it from cooling down and collapsing to form stars. In more extreme cases, the black hole can drive enormous galactic winds, effectively blowing the star-forming gas right out of the galaxy. This deprives the galaxy of its future stellar fuel, causing it to age and turn red as its existing stars grow older without new, blue stars being born to replace them. This negative feedback acts as a crucial self-regulation system. The black hole feeds on the gas, grows in mass, and then uses its own energy to heat or expel the remaining gas, ultimately starving itself and halting its own growth. This elegant balance explains why we don't see galaxies growing infinitely large, and why the mass of the black hole is so closely tied to the mass of the galactic bulge. They grew together, and the black hole ultimately put a limit on further growth for both itself and its host. Given their nature as perfect traps for light, the very idea of observing a black hole directly might seem like a paradox. How can we study something defined by its invisibility? This leads us to our 11th fascinating fact. Astronomers have developed an entire toolbox of ingenious, indirect methods to detect and understand these dark giants, turning their profound influence on the universe into a detailed map of their properties. We don't see the black hole itself, we see the breathtaking choreography it forces upon everything around it. The most straightforward method, and one that provided some of the earliest compelling evidence, is to simply watch how stars behave in its presence. For decades, astronomers have trained their most powerful telescopes on the dense center of our own Milky Way, patiently tracking the paths of individual stars. What they observed was a frantic, high-stakes dance. These stars whip around an invisible point at speeds exceeding thousands of kilometers per second, tracing elongated elliptical orbits over periods of years. Using the simple laws of orbital mechanics established by Kepler and Newton, scientists can analyze these paths. By measuring a star's orbital period and the semi-major axis of its ellipse, they can calculate the mass of the object it's orbiting. The result for our galactic center was undeniable. The stars were dancing around a single, invisible object with a mass of 4 million suns, confined to a region of space smaller than our solar system. This was the first direct dynamical proof of Sagittarius, a star's true nature. When a black hole is active, however, it announces its presence with a blinding flash of light. This is where studying the accretion disk becomes our most valuable window. As matter spirals inward, it is heated to millions of degrees by immense friction and gravitational forces, causing it to glow brilliantly across the entire electromagnetic spectrum. By analyzing this light, astronomers can learn a tremendous amount. The specific wavelengths of radiation, from radio waves to energetic X-rays, tell us about the temperature and composition of the accreting material. Furthermore, the flickering and variability of this light, often changing over remarkably short timescales, indicates the size of the region producing it. Rapid fluctuations mean the emitting area must be compact, pointing directly to the incredibly small volume around the event horizon. Spectroscopic analysis also reveals the Doppler shifts of the hot gas, showing one side of the disk rotating toward us blue shifted, and the other side rotating away red shifted, allowing us to literally map the disk's rotation and velocity. For the most distant black holes, nature provides its own magnifying glass through an effect called gravitational lensing. This phenomenon occurs when the immense gravitational field of a black hole, or its host galaxy, warps the spacetime around it so severely that it acts like a cosmic lens. Light from a more distant star or galaxy passing close to this gravitational well is bent and distorted on its way to our telescopes. This can create multiple images of the background object, stretch it into dramatic arcs, or amplify its brightness. By studying this distortion, astronomers can precisely measure the mass of the foreground object causing the lensing, including the contribution of its central black hole. It's a method that uses Einstein's theory of relativity itself to weigh the most massive objects in the universe. The pinnacle of this indirect detection, however, was achieved in April 2019, when the Event Horizon Telescope collaboration did the seemingly impossible. They presented the world with the first direct image of a black hole's shadow. This was not a photograph of the black hole itself, but of its silhouette against the brilliant backdrop of its accretion disk. The HT is not a single telescope, but a global network of radio observatories working in unison using a technique called very long baseline interferometry. By synchronizing data from telescopes across the globe, they created a virtual Earth-sized antenna, achieving a resolution sharp enough to read a newspaper in New York from a cafe in Paris. This incredible resolution was necessary to resolve the shadow of the supermassive black hole at the heart of the galaxy Messier 87, a void 55 million light-years away. The image revealed a bright, asymmetric ring of hot gas, the accretion disk, and at its center, a dark region. This darkness is the black hole's event horizon, the point where light vanishes, its shadow cast against the fiery maelstrom behind it, providing humanity with its most direct and awe-inspiring view of the universe's most enigmatic object. But while the accretion disk represents matter's final, glowing descent, some supermassive black holes also perform a feat of cosmic defiance, violently ejecting a fraction of that infalling material back out into the universe with unimaginable force. These are relativistic jets, and they rank among the most spectacular and powerful phenomena in the cosmos. Unlike the spherical outbursts of energy, these jets are exquisitely focused beams, firing from the black hole's poles at nearly the speed of light and often stretching for millions of light-years, far beyond the boundaries of their own galaxies, carving paths through the intergalactic void. The creation of these colossal beams is a testament to the raw power of physics operating at its most extreme. It begins with the black hole's incredible spin, which twists the fabric of space-time around it into a vortex, and the intensely powerful magnetic fields generated by the churning, ionized gas of the accretion disk. As this magnetized plasma spirals inward, The black hole's rotation winds these magnetic field lines into an incredibly tight helical structure, like twining a rope tighter and tighter until it's ready to snap. This creates a narrow corridor along the black hole's rotational axis, a channel of focused magnetic energy that acts as a colossal particle accelerator. Within this magnetic nozzle, charged particles are gripped and slingshotted outward. Protons and electrons are accelerated to velocities so close to the speed of light that the concepts of time and space change for them. As these particles race along the magnetic field lines, they emit radiation across the entire spectrum, from radio waves to gamma rays, a process known as synchrotron radiation that makes the jets shine brilliantly against the blackness of space. The efficiency of this process is staggering. The energy transferred from the black hole's spin into the kinetic energy of the jet can convert the mass of a single asteroid into more energy than our Sun will produce in its entire 10 billion-year lifespan. The sheer scale of these structures is what truly defies human comprehension. The jet erupting from the central black hole of the galaxy Messier 87, which we've now famously imaged, extends for at least 5,000 light-years from its host. But that is merely a nearby example. The jets from more distant quasars have been observed to span distances that are almost impossible to grasp. The quasar known as S50014+81 has a jet measured at over 1.5 million light-years in length. To put that in perspective, our entire Milky Way galaxy is only about 100,000 light-years across. This single jet emanating from one object is 15 times longer than our entire home galaxy, a searchlight beam of energy that punches through intergalactic space, influencing everything in its path. These jets are far more than just spectacular light shows. They are fundamental agents of change on a galactic scale. When a jet plows into the tenuous gas that exists between galaxies within a cluster, it does not simply pass through. It deposits immense energy, heating the gas and preventing it from cooling and collapsing to form new stars. This is a primary way a supermassive black hole regulates the growth of its own galaxy and its neighbors. In some cases, the jets can even trigger star formation by compressing cold gas clouds with their powerful shock waves as they expand. They are the primary delivery system for a black hole's feedback, a cosmic thermostat that controls the climate of star birth for millions of light-years in every direction, proving that even in its most destructive acts, a black hole can also be a force of creation. But for all the brilliant light and energy we can observe, black holes present physics with perhaps its most profound and unsettling mystery, a puzzle so deep it strikes at the very heart of our understanding of reality. This is the black hole information paradox, a conflict between the two most successful pillars of modern physics, Einstein's theory of general relativity and the quantum mechanics that govern the subatomic world. The question seems simple on its surface. When an object falls into a black hole, what ultimately happens to all the information that described it, its mass, its charge, its spin, the arrangement of its atoms, every detail that made it unique? According to the pure classical gravity of general relativity, the answer is terrifyingly straightforward. That information is lost forever, irretrievably erased from our universe. Once something crosses the event horizon, every trace of its identity is crushed into the featureless singularity, adding only to the black hole's total mass, spin, and charge. The universe, in this view, is the ultimate shredder. If you were to throw a perfectly detailed encyclopedia into a black hole, all the knowledge it contained would be reduced to 3 simple numbers, making the black hole very slightly more massive, causing it to spin a tiny bit faster, or changing its charge by an infinitesimal amount. This idea that the universe could simply forget information is not just strange, it violates a fundamental tenet of quantum mechanics. Quantum theory is built on the principle of unitarity, which essentially states that information is never truly destroyed. It can be scrambled, spread out, and become incredibly difficult to read, like mixing paints together. but in principle it is always preserved. If you knew the exact state of every particle in that mixed paint, you could theoretically reverse the process and separate them back into pristine colors. The quantum view of the universe is that it is predictable and reversible at its core. Information is eternal. The classical black hole view suggests the universe is inherently unpredictable and forgetful. This is the paradox. Two of our most powerful theories give completely contradictory answers to a basic question. The conflict was brought into sharp focus by Stephen Hawking's revolutionary work in the 1970s. By applying quantum theory to the curved spacetime right at the edge of a black hole's event horizon, Hawking made a stunning prediction. Black holes are not completely black. They should slowly emit a faint glow of particles, now known as Hawking radiation. This radiation, he argued, is entirely random and thermal, carrying no information about what fell into the black hole. It's like the heat radiating from a warm piece of coal. It tells you the temperature, but nothing about how the coal was formed. As this radiation streams away, the black hole slowly loses mass and evaporates. Hawking's calculation suggested that after an unimaginably long time, a black hole would completely vanish, leaving behind nothing but this random thermal radiation. The original encyclopedia and every other bit of information that ever fell in would be truly and permanently erased from existence, a notion that horrified physicists and became known as the information paradox. Hawking's proposal sparked a decades-long debate that continues to this day, often summarized by the pithy question: does Hawking radiation violate quantum mechanics? The physics community has largely sided with quantum mechanics, believing that information must be preserved, even if we don't yet understand how. The current leading idea, the holographic principle, proposes that all the information about objects that fall into a black hole is not lost inside, but is somehow encoded on its two-dimensional event horizon, like a cosmic fingerprint smeared across its surface. As the black hole evaporates via Hawking radiation, this information is somehow imprinted onto the escaping particles, slowly and chaotically leaking back out into the universe. Solving this paradox may require a theory of quantum gravity, a way to seamlessly merge general relativity with quantum mechanics, and could reveal that our universe operates in a way far stranger and more magnificent than we ever imagined. For all our detailed understanding of stellar mass black holes and the undeniable presence of their supermassive cousins, astronomers have long been puzzled by a glaring gap in the cosmic family tree. We have compelling evidence for black holes weighing just a few times the mass of our Sun, formed from the collapse of massive stars, and we are surrounded by proof of the supermassive giants, weighing millions or billions of solar masses anchoring galactic centers. But what about the middle children? Where are the black holes of intermediate mass, the crucial missing link that could explain how the small ones grow into the cosmic behemoths? This search for intermediate mass black holes has become one of astronomy's most compelling detective stories. The hunt is so difficult because these objects are inherently elusive. An intermediate mass black hole, which might weigh anywhere from 100 to 100,000 solar masses, possesses a gravitational pull that is powerful but not overwhelmingly so. If it's not actively feeding on a large cloud of gas, it won't have a brilliant, shining accretion disk to give away its position like a quasar does. And if it's sitting alone in the dark emptiness between stars, there are no rapidly orbiting stars for us to track, no dramatic stellar dance to observe. It could be a dark ghost drifting silently through a star cluster or the halo of a galaxy, its presence betrayed only by the subtlest of gravitational whispers. Some of the most promising places to look for these missing links are within dense globular clusters, ancient spherical collections of hundreds of thousands of stars that orbit the outskirts of galaxies like our Milky Way. The core of such a cluster is a chaotic environment where stars interact gravitationally. and theorists suggest that repeated collisions and mergers could build up a black hole of several hundred or even a few thousand solar masses over time. For years, evidence was circumstantial and unusual concentration of X-rays from a cluster's core, or stars that seemed to be moving just a bit too fast. Then, in 2020, astronomers made a breakthrough discovery using the Hubble Space Telescope. They were studying the globular cluster Omega Centauri, a vast swarm of stars, and noticed a group of stars at its very center moving at inexplicably high speeds. The only thing that could explain this frantic motion was the gravitational pull of a concentrated, invisible mass, the calculated mass of this hidden object. Around 40,000 times that of our Sun, this was not a stellar remnant, this was a bona fide intermediate mass black hole, the first strong candidate of its kind. The significance of finding this missing link extends far beyond simply completing a classification chart. Intermediate mass black holes are the prime suspects for being the seeds from which supermassive black holes grew. In the early universe, the first stars were colossal and short-lived, collapsing directly into black holes of perhaps a few hundred solar masses. For a single one of these to grow into a billion solar mass quasar in the relatively short time we see them in the ancient cosmos, it would have had to feed at a physically impossible rate, gobbling up matter continuously without pause. But if those early seeds were instead intermediate mass black holes, already weighing thousands of solar masses from the start, their path to becoming supermassive is far more plausible. They could have grown through a combination of feeding on gas and, crucially, merging with other intermediate mass black holes during galactic collisions. Each merger would create a larger black hole, building mass exponentially through these cosmic unions. Finding them today is like finding the primordial building blocks of the giants that now rule the centers of galaxies, offering us a living fossil record of how the most massive structures in the universe first came to be. Even the most cataclysmic events in the cosmos, like the merging of supermassive black holes, would seem to occur in utter silence to our human senses, playing out in the perfect vacuum of space where sound cannot travel. Yet, these titanic collisions do not go unheard. They cause the very fabric of the universe to ring like a colossal bell, generating a vibration that hums at a frequency far below anything our ears could perceive. This is the song of spacetime itself, a phenomenon predicted by Einstein a century ago but only recently confirmed: gravitational waves. Imagine spacetime not as a static stage, but as a flexible, invisible fabric like the taut surface of a trampoline. When any object with mass rests on this fabric, it creates a depression. Now, imagine two incredibly dense objects like black holes orbiting each other. As they spiral inward, their immense masses whip through this cosmic fabric, sending out ripples, waves of distortion that travel outward at the speed of light. These are gravitational waves. They are not waves in space, they are waves of space itself, rhythmically stretching and squeezing the distance between everything in their path as they pass by. When two supermassive black holes finally merge, the resulting blast of these waves is the most powerful single event since the Big Bang, briefly releasing more energy than all the stars in the observable universe combined. Detecting these faint cosmic whispers required one of the most precise experiments ever conceived: the Laser Interferometer Gravitational Wave Observatory, or LIGO. Each LIGO facility consists of two 4-kilometer long vacuum tubes arranged in an L shape. A single laser beam is split and sent racing down each arm, bouncing off perfectly suspended mirrors at the end to race back and recombine. Under normal conditions, the light waves cancel each other out, but when a gravitational wave passes through Earth, it minutely changes the length of one arm relative to the other by a distance thousands of times smaller than the nucleus of an atom. This infinitesimal change alters the laser light's path, causing the waves to no longer cancel perfectly and creating a flicker of light that is detected, a direct signature of spacetime itself quivering. The first historic detection in 2015 was not from supermassive black holes, but from a pair of stellar mass black holes merging over 1 billion light-years away. The signal, translated into an audible sound, was a distinct chirp, a rapid increase in frequency and amplitude as the black holes spiraled ever faster before culminating in a final, ringing bang of their union. This single chirp confirmed Einstein's theory and opened an entirely new window on the universe, a form of astronomy that listens to the vibrations of spacetime rather than looking for light. Since then, observatories like Virgo in Italy and Kagra in Japan have joined this global network, allowing scientists to triangulate the sources of these waves and pinpoint their origin in the sky. For supermassive black holes, the song is a much deeper, lower-frequency hum, one that requires a different kind of observatory altogether. Projects like Nanograv use pulsars incredibly dense, rapidly spinning neutron stars that act as cosmic lighthouses, emitting beams of radio waves with metronomic precision. By meticulously monitoring the arrival times of these pulses from an array of pulsars across the galaxy for over a decade, astronomers can detect the subtle, correlated shifts caused by the persistent background hum of gravitational waves from countless merging supermassive black holes throughout the universe. It's the chorus of all the supermassive black hole binaries in the cosmos, a low-frequency rumble that fills the universe, allowing us to sense the slow, gravitational dance of giants too distant and too long-lived for us to witness individually. What these cosmic vibrations reveal is nothing short of revolutionary. By analyzing the specific waveform of a gravitational wave signal, scientists can directly calculate the masses and spins of the black holes that created it, properties that are often impossible to determine through light alone. This data provides an unbiased census of black holes throughout the cosmos, helping us understand how they form and find each other to merge. Furthermore, because gravitational waves travel unimpeded through matter, they allow us to probe the darkest, most obscured regions of the universe, like the chaotic hearts of merging galaxies, giving us a clear view of events that optical telescopes could never hope to see. Each detected wave is a direct message from the warped depths of gravity itself, telling the story of a violent union and providing a new, fundamental tool to map the hidden structure of our universe. While the immense gravity of supermassive black holes shapes the visible cosmos, their story may be deeply intertwined with the universe's most elusive substance, dark matter. This invisible material, which makes up over 85% of all matter in the universe, does not emit, absorb, or reflect light, revealing its presence only through its gravitational influence on galaxies. The 16th remarkable fact we explore is the compelling, though still theoretical, connection between these dark matter halos and the supermassive black holes that reside at galactic centers, suggesting a cosmic partnership that governs the growth of the largest structures in the universe. The relationship begins with the very formation of galaxies. Current models of cosmic evolution suggest that dark matter acted as the primordial scaffolding for all visible structure. After the Big Bang, slight fluctuations in the density of dark matter began to collapse under their own gravity, forming vast, invisible halos. The gravitational pull of these halos then attracted ordinary baryonic matter, the gas that would eventually form stars, planets, and us. This means every galaxy, including our Milky Way, is embedded within a much larger sphere of dark matter, a cosmic framework that dictates its shape and size. The intriguing question for astronomers is whether the size and mass of this dark matter halo directly influence the development of the central supermassive black hole. Some theories propose that larger, more massive halos provided a deeper gravitational well, funneling more gas toward the center and thereby feeding and growing a more massive black hole, potentially explaining the tight correlation between black hole mass and galactic properties. Beyond just formation, dark matter might also play a direct role in fueling a black hole's growth through a fascinating, albeit speculative, mechanism. In the dense center of a galaxy, the concentration of dark matter particles could be extremely high. Some models suggest that when two dark matter particles collide, they could annihilate each other, converting their mass directly into energy according to Einstein's famous equation. This injection of pure energy could heat the surrounding gas, preventing it from cooling and forming stars, and instead making it more available for the black hole to consume. In other words, the annihilation of dark matter might act as a power source that indirectly feeds the accretion disk, providing a steady trickle of fuel that helps a black hole maintain its activity over billions of years, even in galaxies where the visible gas supply seems limited. Perhaps even more astonishing is the possibility that black holes themselves could be our most powerful tools for finally detecting and understanding dark matter. The environment immediately around a supermassive black hole is one of the most extreme in the universe, and its intense gravity could dramatically increase the density and collision rate of dark matter particles in its vicinity. This would make the region a natural laboratory for dark matter annihilation, potentially creating a unique signature of gamma rays or other high-energy radiation that our telescopes could detect. By carefully observing the emission from the vicinity of black holes, especially those that are relatively quiet and not obscured by bright accretion disks, astronomers hope to find the unmistakable fingerprint of dark matter interactions, using the black hole's gravity as a magnifying glass to illuminate the invisible. This profound interconnection suggests that the largest black holes are not just inhabitants of their galaxies, but may be integral components of a larger, dark matter-driven ecosystem. Their growth, activity, and very presence could be a direct consequence of the invisible cosmic architecture that constitutes the true bulk of our universe. Unraveling this relationship stands as one of the most exciting frontiers in astrophysics, a puzzle where understanding the darkest objects in the cosmos might be the key to shedding light on its deepest secret. Looking far beyond our own solar neighborhood, the challenge of navigating the immense void between stars becomes a monumental problem. Our familiar constellations would be useless, and the sun would shrink to just another point of light in a sea of thousands. For future interstellar travelers, finding their way would require something far more constant and reliable than stars. This is where the universe's most predictable clocks and its most massive gravitational anchors could provide an ingenious solution. The 17th incredible fact is that supermassive black holes, in concert with the precise ticks of pulsars, could one day form the backbone of a cosmic navigation network, a galactic GPS for voyages between the stars. The concept hinges on using the universe's most stable and recognizable landmarks as reference points. At the heart of this system would be pulsars, the rapidly spinning, ultra-dense corpses of massive stars that have gone supernova. These neutron stars emit beams of radiation from their magnetic poles, and as they rotate, these beams sweep across space like a lighthouse. If the beam points toward Earth, we detect a highly regular pulse of radio waves. Some pulsars, especially millisecond pulsars, spin hundreds of times per second with a stability that rivals atomic clocks. Their rhythmic pulses are so predictable that we can calculate their arrival times years in advance with incredible accuracy. A spacecraft could carry a database of these expected pulse patterns for known pulsars across the galaxy. By measuring the actual arrival time of these pulses and comparing it to the expected time from its onboard database, the spacecraft could triangulate its position, much like how GPS satellites on Earth use timing signals from multiple sources to calculate a location. But pulsars alone have a limitation. They are moving through space themselves. While incredibly stable in their rotation, their positions relative to each other can drift over very long timescales. This is where supermassive black holes come in, serving as the fixed anchor points for this entire celestial navigation grid. Recall that nearly every large galaxy has a supermassive black hole at its absolute center. These objects are the most massive, stable, and unmoving gravitational landmarks in the entire universe. Their positions define the true center of their galaxies. For a spacecraft navigating the Milky Way, our own central black hole, Sagittarius, a star, would be the ultimate reference point, the true north of our galactic compass. Its position is fixed at the galactic core, providing a constant, unwavering anchor against which all other motions, including those of the pulsars, can be measured and calibrated. A practical navigation system would likely work by using a combination of these references. A spacecraft's computer would continuously monitor the signals from a network of perhaps a dozen known millisecond pulsars, each acting as a separate beacon. It would then use the known, fixed position of Sagittarius, a star, as a base correction point to account for any tiny long-term drifts in the pulsar positions themselves. By cross-referencing the timing differences from multiple pulsars against the central black hole's anchor, a ship's navigation computer could calculate its precise three-dimensional location within the galaxy, its velocity, and even its orientation, all without any need for communication with Earth. This autonomy would be crucial for missions decades or centuries long, where waiting for a signal from home that takes years to arrive would be utterly impractical. The development of such a system isn't just science fiction. It's already being tested in a preliminary form. NASA's NICER experiment on the International Space Station has been conducting pioneering work in what they call Station Explorer for X-ray timing and navigation technology, or sextant. This experiment uses X-ray telescopes to detect the regular pulses from pulsars, demonstrating the fundamental principle that their timing can be used to determine a position in space accurately. While our current efforts are focused within our solar system, the underlying physics scales up to the entire galaxy. The steady, relentless clockwork of pulsars, anchored by the immutable presence of supermassive black holes, could one day provide the guidance that allows humanity to venture out among the stars, turning the darkest and most massive objects in the cosmos into the beacons that light our way home. Stephen Hawking's most revolutionary contribution to our understanding of black holes wasn't about how big they could grow or how they merged, but about how they could potentially die. He turned the entire concept of a black hole on its head by proposing that these ultimate prisons are not entirely black after all. In a stunning theoretical leap that merged the physics of the very large with the laws of the very small, Hawking showed that black holes should glow with a faint light, slowly leaking their mass back out into the universe in a process that would take longer than the current age of the cosmos to complete. This phenomenon, now known as Hawking radiation, arises from a bizarre but fundamental quirk of quantum mechanics. The universe is never truly empty, not even in the perfect vacuum of space. At the tiniest scales, pairs of virtual particles constantly flicker in and out of existence, borrowing energy from the vacuum for an immeasurably short time before annihilating each other and paying that energy back. This is happening everywhere all the time. Normally, this quantum froth is undetectable and has no net effect, but place this process at the very edge of a black hole's event horizon, and something extraordinary happens. Imagine one of these particle-antiparticle pairs spontaneously appearing right at the precipice. In the fraction of a moment before they annihilate, the immense gravitational tidal forces of the black hole can rip them apart. One particle falls across the event horizon, forever lost to the outside universe, while its partner is ejected outward, escaping as real radiation. From the perspective of an outside observer, the black hole has just emitted a particle. To conserve energy, the particle that fell in must have had negative energy relative to the outside world. This effectively reduces the mass of the black hole by a tiny amount. The black hole has paid the energy cost for creating the real, escaping particle with a sliver of its own mass. This isn't a violent, explosive process. It's an incredibly slow and faint trickle. The temperature of this Hawking radiation is inversely related to the black hole's mass. For a stellar mass black hole, the temperature is a tiny fraction of a degree above absolute zero, making the radiation utterly negligible and impossible to detect against the cosmic microwave background. For a supermassive black hole, the temperature is even colder. The rate of evaporation is so slow that a black hole with the mass of our Sun would take 10 to the 67 years to evaporate, a number so vast it dwarfs the current age of the universe, which is only 13.8 billion years. This timescale is truly astronomical, far longer than any other physical process we know. The ultimate fate of an isolated black hole, given enough time, is to slowly shrink. As its mass decreases, its temperature paradoxically increases, and the rate of Hawking radiation accelerates. In the final moments of its evaporation, when its mass becomes comparable to a small asteroid, the process would become dramatic. The black hole's temperature would soar to billions of degrees, and it would emit a final burst of high-energy radiation across the spectrum, a last brilliant flash signaling the end of an object that may have existed for trillions upon trillions of years. This theoretical end stage poses fascinating questions about information and quantum gravity, as the complete evaporation of a black hole would seemingly violate quantum principles if the information about everything it ever consumed is truly lost, a paradox that continues to drive theoretical physics forward. Hawking's discovery revealed that black holes are not eternal. They are dynamic objects with a life cycle, subject to the same quantum rules that govern the rest of reality, slowly returning their borrowed mass to the cosmos one particle at a time. Yet for all their destructive power, black holes might also be the ultimate creators, giving birth to entirely new universes in a process that redefines the very meaning of cosmos. This 19th fact ventures into the most speculative and mind-bending territory of all, where the known laws of physics break down and the fabric of reality itself might be rewoven. Some of the most profound theories in modern cosmology suggest that the extreme conditions within a black hole, particularly at its mysterious singularity, could serve as a bridge to other universes or even act as a cosmic womb from which entirely new realities are born. The gateway to this idea is the singularity itself, that point of infinite density where our current understanding of physics simply stops working. General relativity predicts its existence, but the laws of quantum mechanics, which govern the behavior of the very small, are needed to describe it, and these two theories remain stubbornly incompatible at such extremes. This has led physicists like Stephen Hawking and others to propose that the singularity might not be a point of infinite crushing, but rather a region of unimaginably high but finite density, a place where spacetime is contorted into entirely new forms. In this bizarre environment, the very concepts of before and after could become meaningless, and the distinction between our universe and something else might blur entirely. One compelling, though highly theoretical, idea is that a black hole's singularity might not be an end but a transition, a tunnel in spacetime known as a wormhole. According to some solutions of Einstein's equations, the inward collapse of matter in a black hole could theoretically connect to the outward expansion of a white hole in another region of spacetime, spewing out the ingested material into a different universe or a different time. This would make the black hole not a pit of oblivion but a one-way bridge, a cosmic shortcut through a higher dimension. While stable, traversable wormholes are considered highly unlikely with our current physics due to the need for exotic matter with negative energy to hold them open, the possibility remains that the internal structure of a black hole could inherently contain such a connection, forever hidden behind its event horizon from our perspective. An even more radical proposition is that our entire universe could have been born from such an event in a parent cosmos. This is the concept of cosmological natural selection proposed by physicist Lee Smolin. Imagine a black hole forming in a pre-existing universe, As matter collapses into the singularity, the insane pressures and temperatures could trigger a bounce, not unlike the theoretical Big Bounce that might have preceded our own Big Bang. This bounce would not reverse the collapse, but instead would spawn an entirely new universe from the singularity, expanding into its own dimensions with its own fundamental constants and physical laws. In this breathtaking scenario, every black hole in our universe could be the Big Bang of a separate daughter universe, hidden within its own space-time bubble. The laws of physics in these offspring universes might be slightly different from our own, perhaps with variations in the strength of gravity or the mass of electrons, determined by the specific conditions of the parent black hole. This idea paints a picture of a vast multiverse, a cosmic evolutionary tree where universes that produce more black holes, more offspring, are naturally selected for as they create more opportunities for new universes to exist. Our own universe, with its perfect conditions for forming stars and black holes, might itself be a product of such a selection, fine-tuned for fecundity rather than for life, offering a stunningly elegant and purely physical explanation for why the constants of nature seem so perfectly set for our existence. While these ideas remain at the frontier of theoretical physics, they transform black holes from mere monsters into potential architects of cosmic genesis, suggesting that death and rebirth on a universal scale might be intertwined in the deepest darkness of space. These ancient giants, known as supermassive black holes that existed when the universe was less than 1 billion years old, present one of the most pressing and fascinating puzzles in modern cosmology. How could such colossal objects, weighing over 1 billion solar masses, form in what amounts to the cosmic blink of an eye after the Big Bang? The existence of these early behemoths pushes our understanding of physics to its very limits and forces us to reconsider the fundamental processes of cosmic growth. Discovering these objects was a triumph of observational astronomy, made possible by peering back across nearly the entire history of the universe. Using powerful instruments like the James Webb Space Telescope and large ground-based observatories, astronomers scan the most distant reaches of space. Because light takes time to travel, looking far away means looking back in time. The most distant quasars we observe are seen as they were when the universe was only 600 or 700 million years old, a mere 5% of its current age. Yet their light reveals the unmistakable signature of a supermassive black hole already in place, blazing with the energy of 1 billion suns. The quasar J1342 plus 0928, for instance, is seen just 690 million years after the Big Bang and harbors a black hole with a mass over 800 million times that of our Sun. The sheer size of these early black holes creates a significant timing problem known as the seeding problem. Let's walk through the math. A black hole feeding at the maximum possible rate, a state known as Eddington limited accretion, can only grow so fast without radiation pressure from its own luminosity blowing away the very gas it's trying to consume. Even if a black hole started from a massive seed and fed continuously at this maximum rate for 700 million years, calculations show it could only reach a few 100 million solar masses. Yet we observe black holes that are several times larger than this theoretical limit. They must have either started from unimaginably large seeds, far larger than any star could produce, or found a way to consume matter at super Eddington rates, defying our standard models of physics. This conundrum has led astrophysicists to propose some truly extraordinary formation mechanisms for these primordial seeds. Perhaps they weren't born from the first stars at all. One compelling theory suggests that in the early universe before the first stars ignited, enormous clouds of pristine hydrogen and helium could have collapsed directly under their own gravity, bypassing star formation entirely and imploding into black holes containing tens or even hundreds of thousands of solar masses from their very inception. These direct collapse black holes would have been born large, giving them a massive head start on their growth. Another possibility is that the earliest, incredibly dense star clusters experienced runaway collisions, with massive stars merging again and again to form a single gigantic object that then collapsed into a substantial seed black hole. The environment of the early universe was uniquely suited for such rapid growth. Space was much smaller and denser, with gas clouds packed tightly together and not yet enriched by heavy elements from previous generations of stars. This pure hydrogen gas may have been able to flow inward more efficiently, cool faster, and avoid the feedback processes that slow black hole growth in modern galaxies. It's possible that in this cosmic nursery, the rules were different, allowing for brief periods of hyper-efficient, super-Eddington accretion where black holes could gorge themselves on a vast buffet of available matter, doubling their mass in just a few million years instead of the tens of millions required by standard models. Studying these ancient leviathans is more than an academic exercise. It's a direct window into the conditions of the infant universe. Their very existence tells us that the early cosmos was a place of extreme physics and rapid transformation, where gravity worked on an accelerated timetable to build the largest structures we know. Each new discovery of an early quasar pushes the timeline of formation further back, challenging our models and inspiring new theories about the dawn of cosmic structure. These black holes are not just ancient relics. They are the pioneers that illuminated the cosmic dark ages and began the process of shaping the galaxies that would eventually fill the universe. While the supermassive black holes at the hearts of galaxies often feed on a steady diet of gas and dust, their most spectacular and violent meals occur when an entire star strays too close. This 21st fact reveals one of the most dramatic events in the cosmos. A tidal disruption event, a celestial catastrophe where a black hole's gravitational power literally rips a star to shreds. These cosmic fireworks are not just brutal displays of force, they are brilliant beacons that allow astronomers to study otherwise dormant black holes and measure their properties with incredible precision. The fate of a star in this scenario is determined by a simple but critical threshold known as the tidal radius. This is the distance from the black hole where the difference in gravitational pull on the near and far sides of the star, the tidal force, overcomes the star's own gravity, the force that holds it together. For a star like our Sun approaching a supermassive black hole, this point of no return is typically well outside the event horizon. As the star crosses this boundary, it experiences an immense stretching force. The side of the star closer to the black hole is pulled much more strongly than the far side, elongating the star into a thin stream of gas in a process picturesquely known as spaghettification. This isn't a sudden snap, but a gradual and horrifying unraveling, where a sphere of luminous plasma is stretched into a long, thin filament wrapping around the black hole. What happens next is a phenomenal release of energy. About half of the stellar debris is flung away from the black hole at high velocity, while the other half is captured into a swirling, chaotic accretion disk. As this material spirals inward, it is compressed and heated to temperatures of hundreds of thousands of degrees, causing it to shine with incredible brilliance across the electromagnetic spectrum, from visible light to X-rays. This produces a characteristic flare that can outshine the combined light of every star in the host galaxy for weeks or even months. This bright flash is the signal astronomers hunt for, a transient event that screams the location of a previously hidden black hole and details of its recent feast. The specific characteristics of this flare are a treasure trove of information. The rise time of the flare, how quickly it reaches peak brightness, tells us about the mass of the black hole. More massive black holes have larger tidal radii, so they disrupt stars further out. The debris then takes longer to fall back and create the bright accretion disk, resulting in a slower, more gradual brightening. The luminosity and duration of the flare reveal the mass of the star that was consumed. A larger star provides more fuel, leading to a brighter and longer-lasting event. By carefully analyzing the light curve and spectrum of a tidal disruption event, scientists can effectively weigh the black hole, determine the type of star it destroyed, and understand the physics of how matter behaves under the most extreme gravitational conditions imaginable. These violent encounters transform quiet, invisible giants into temporary beacons, allowing us to take a census of dormant black holes across the universe and witness the awesome power of gravity in its most raw and destructive form. Yet for all their physical ferocity and cosmic spectacle, the true nature of black holes is ultimately revealed not through images or explosive events, but through the serene and precise language of mathematics. The equations that describe these gravitational giants are not just dry formulas. They are profound expressions of the universe's underlying order, predicting the bizarre properties of black holes with a level of accuracy that borders on the mystical. These mathematical models allow us to comprehend the incomprehensible, providing a window into realities we could never otherwise witness. The journey of understanding began with the Schwarzschild metric, a solution to Einstein's fiendishly complex field equations of general relativity. Discovered by Carl Schwarzschild in 1916, just months after Einstein published his theory, this solution describes the geometry of spacetime around a perfectly spherical, non-rotating, and uncharged black hole, what we now call a Schwarzschild black hole. The equation itself is a thing of stark beauty, defining how space stretches and time slows as one approaches the central singularity. It is from this metric that the very concept of the event horizon naturally emerges, not as an assumed barrier, but as a mathematical certainty. At a specific radius, now known as the Schwarzschild radius, the equations produce a singularity, a sign that our coordinates break down and that this boundary represents a point of no return. This elegant piece of mathematics single-handedly predicted the existence of black holes as physical objects years before the term was even coined, demonstrating the incredible power of pure thought to reveal the deepest secrets of the cosmos. But the universe is rarely so simple as to be perfectly still. Most cosmic objects, including the supermassive black holes at galactic centers, rotate, and this spin introduces a whirlpool-like complexity to the fabric of spacetime. For decades, the Schwarzschild solution was the only known answer, and physicists struggled to find a way to describe a spinning black hole within Einstein's framework. The breakthrough came in 1963 from New Zealand mathematician Roy Kerr. His solution, the Kerr metric, is widely regarded as one of the most exquisite and important in all of theoretical physics. It describes the spacetime around a rotating black hole with breathtaking completeness. The Kerr solution is far more than just Schwarzschild plus spin. It introduces a breathtaking array of new phenomena. The equations naturally predict the formation of an ergosphere, an oval-shaped region of distorted spacetime outside the event horizon where nothing can remain stationary. It is here that the black hole's rotational energy is stored and can, in theory, be extracted. The mathematics also reveals that a rotating black hole has not one, but two event horizons, and that the singularity at its center is not a point but a ring, a one-dimensional loop where the known laws of physics cease to apply. Perhaps most astonishingly, the Kerr metric suggests the possibility of a Kerr wormhole, a gateway through the ring singularity that could theoretically connect to another universe or another time, though traversing it remains firmly in the realm of speculation. The incredible precision of Kerr's solution is confirmed every time we observe the orbital periods of stars around Sagittarius, a star, or the properties of accretion disks. Reality behaves exactly as his mathematics predicted over half a century ago. The power of these equations lies in their stunning economy. From the deceptively simple fabric of spacetime curvature described by Einstein, physicists can derive every major property of a black hole using nothing more than pencil, paper, and the power of logic. The mass and spin of a black hole completely determine its entire character. the size of its event horizon, the shape of its ergosphere, the orbital paths of nearby matter. This concept is poetically summarized by the no-hair theorem, which states that black holes are remarkably simple objects defined by just three properties: mass, electric charge, and angular momentum or spin. They have no other distinguishing features or hair. All other information about the material that formed them or that they have consumed is irretrievably lost behind the event horizon, hidden from the external universe. This mathematical simplicity emerging from such physical complexity is a profound reminder that at the heart of the universe's most terrifying monsters lies an elegant and beautiful order, a set of rules written in a language of geometry that we are only just beginning to fluently read. But as we peer billions, even trillions of years into the future, a profound and humbling destiny emerges for these cosmic giants. In the unimaginably distant epochs to come, long after the last stars have flickered out and the cosmic background radiation has faded to a whisper, black holes will inherit the universe. They will become the final sentinels in a dark, expanding void, the last recognizable structures in a cosmos sliding toward maximum entropy. This ultimate fate is not one of dramatic collapse, but of a slow, inexorable fade driven by the faintest of quantum whispers. The timeline for this cosmic evolution is almost beyond human comprehension. For trillions upon trillions of years, the universe will be in the stelliferous era dominated by stars. But even stars have a finite fuel supply. The most massive stars burn brightly and die quickly in supernova explosions, leaving behind neutron stars and black holes. Lower mass stars like red dwarfs are far more frugal, shining faintly for up to 10 trillion years. Eventually, however, the raw material for new star formation will be exhausted. Galaxies will stop making new stars, and the existing ones will gradually burn out. The universe will enter what astronomers call the degenerate era, a time dominated by the cooling remnants of stars, white dwarfs, neutron stars, and black holes. These objects will drift through an ever-cooling and expanding space, their gravitational interactions occasionally triggering faint flashes of light as they collide or disrupt planets, but for the most part, the universe will be a very dark place. During this immensely long period, supermassive black holes will remain the dominant gravitational forces, but even their era of feasting will be over. With no gas clouds to consume and no stars to tear apart, they will sit silently at the centers of dead galaxies, their immense mass governing the slow, stately dance of the stellar remnants around them. Their only source of sustenance will be the rare, random capture of a passing brown dwarf or a cold, dead planet, events that will become exponentially rarer as the universe continues to expand and matter spreads further apart. For a time scale that makes the current age of the universe seem like a mere blink of an eye, these black holes will be the sole keepers of gravitational order in a profoundly dark and quiet cosmos. Yet, even these ultimate survivors are not eternal. Their demise is dictated by the same quantum process that gives them a faint glow, Hawking radiation. As we discussed, a black hole slowly loses mass by emitting particles from its event horizon. The rate of this evaporation is inversely proportional to its mass. For a supermassive black hole, the process is so agonizingly slow it is practically negligible. A black hole with the mass of our Sun would take 10 to the 67 years to evaporate. But a typical supermassive black hole, weighing millions or billions of solar masses, faces a timeline that is truly astronomical. We are talking about time scales like 10 to the 100th power years, a number so vast it is written as a 1 followed by 100 zeros. The final stages of this evaporation, when they finally arrive, will be the last noteworthy events in the cosmos. As a black hole's mass decreases, its temperature increases and the rate of Hawking radiation accelerates. In its final second of existence, a black hole with the mass of a small mountain would release the energy equivalent of 1,000,000,000,000 megaton nuclear bombs in a tremendous burst of particles and high-energy gamma rays. This final flash will be a brief, brilliant punctuation mark in an otherwise dark and silent universe, a last testament to an object that had persisted for timescales beyond human imagination. After this, nothing will remain but a diffuse, ever-cooling sea of subatomic particles and radiation, stretching thinner and thinner across an infinite and eternal void, a state known as the heat death of the universe. In this grand cosmic narrative, black holes are not just monsters or engines. They are the universe's final chapters, the last objects to hold onto structure and meaning before the long, dark night settles in for good. Yet the immense power and strange physics of these colossal objects also reveal the boundaries of our current understanding, creating a frontier where our most successful theories begin to fray and contradict one another. The behavior of supermassive black holes, particularly in their most extreme states, pushes the laws of physics into uncharted territory, forcing scientists to confront the deepest unsolved problems in fundamental science. The core of this challenge lies in the long-standing and frustrating conflict between the two pillars of modern physics: Einstein's theory of general relativity, which governs the very large and the force of gravity, and quantum mechanics, which governs the very small and the behavior of particles. These two frameworks are spectacularly successful in their own domains, but they are fundamentally incompatible, speaking different mathematical languages and making contradictory claims about the nature of reality. Supermassive black holes, by their very definition, exist at the intersection of these domains. They are immensely massive, requiring general relativity to describe their gravity, and yet all that mass is crushed into a vanishingly small volume, a realm where quantum effects must surely dominate. It is at the event horizon, and most catastrophically at the central singularity, where this conflict becomes an outright war. The event horizon itself presents a subtle but profound puzzle known as the firewall paradox. From the perspective of general relativity, crossing the event horizon of a supermassive black hole should be an unremarkable event for an astronaut. There is no local experiment they could perform to know the precise moment they pass the point of no return, a principle rooted in Einstein's equivalence principle. However, when we apply quantum field theory to this same scenario, a disturbing conclusion emerges. The calculations suggest that the event horizon should not be a smooth region of empty space, but a blazing wall of high-energy radiation, a firewall that would instantly incinerate any object falling through it. This paradox arises from the quantum entanglement of particles implicated in Hawking radiation. The theory suggests that for information to be preserved, as quantum mechanics demands, the entanglement between particle pairs must be violently broken at the horizon, releasing an enormous amount of energy. So, which theory is correct? Is the event horizon a smooth gateway, as Einstein predicts, or a deadly inferno, as quantum mechanics suggests? Resolving this contradiction is not an academic exercise. It forces us to ask fundamental questions about the nature of space, time, and information, and whether our concepts of smooth spacetime can even survive in such an extreme environment. The greatest breakdown, however, awaits at the center, the singularity. General relativity predicts that all the matter that ever fell into the black hole is crushed into a point of infinite density, where the curvature of spacetime becomes infinite and the equations of gravity simply stop working. In mathematics, an infinity in an equation is called a singularity, and it is a clear sign that the theory is incomplete, that it has been pushed beyond its limits of applicability. An infinite density is not a physical concept. It is a signal that we need a new theory, one that can describe gravity in the quantum realm. Physicists refer to this sought-after theory as quantum gravity, a framework that would seamlessly merge general relativity with quantum mechanics. The center of a black hole is the most compelling laboratory for this unknown physics because it is a place where the quantum world and the gravitational world are forced to meet. We cannot observe it directly, but its effects on the surrounding spacetime and the information paradox provide crucial clues. This is why studying the largest black holes is so vital to the future of physics. They are not merely destinations for astronomical observation. They are natural experiments that are testing the laws of physics in ways we could never replicate in a laboratory. By observing how matter behaves as it approaches the event horizon, by measuring the spins and masses of these giants, and by listening to the gravitational waves from their collisions, we are gathering the experimental data that will guide the development of the next great theory. The quest to understand what happens at the singularity is driving the development of candidate theories like string theory and loop quantum gravity, each of which proposes a different fate for the center of a black hole. Some theories suggest the singularity is replaced by a Planck star, a highly dense but finite state of matter, or a bridge to another universe via a wormhole. The extreme nature of supermassive black holes ensures they will remain at the forefront of theoretical physics for decades to come, as they hold the key to unlocking a deeper, more complete understanding of the universe, one that will ultimately rewrite the textbooks and reveal a reality far stranger than we currently imagine. While our largest particle accelerators on Earth, like the Large Hadron Collider, are monumental feats of engineering capable of smashing protons together at nearly the speed of light, they are utterly dwarfed by the natural accelerators operating in the depths of space. The environment surrounding a supermassive black hole is a maelstrom of such intense energies that it can hurl subatomic particles across the universe with a force our greatest machines can only dream of replicating. These particles, known as cosmic rays, are essentially atomic nuclei, mostly protons, that have been accelerated to velocities just a hair's breadth from the ultimate cosmic speed limit. When one of these high-energy particles eventually strikes Earth's atmosphere, it creates a spectacular shower of secondary particles, a silent echo of the violent events that gave it birth billions of light-years away. For physicists, these natural projectiles are invaluable gifts from the cosmos, providing a window into the fundamental laws of nature at energy scales that are completely unattainable in any terrestrial laboratory. The engine behind this incredible process is a combination of the black hole's ferocious gravity and its powerful magnetic fields. As matter spirals inward through the accretion disk, it isn't just heated to incandescence. It is also ionized, meaning its atoms are torn apart into a soup of charged particles like protons and electrons. This plasma becomes caught in the grip of the black hole's immensely powerful magnetic field, which is generated and amplified by the churning motion of the disk itself. Imagine these magnetic field lines as invisible, incredibly taut rubber bands threading through the chaos. When a charged particle interacts with this field, it doesn't just get a gentle push, it can become trapped, bouncing back and forth between magnetic mirrors, gaining a tremendous amount of energy with each pass in a process known as Fermi acceleration. In some cases, particles can be caught in the magnetic vortex and slingshotted along the polar jets, those narrow beams of plasma erupting from the black hole's poles. Traveling along these magnetic corridors, the particles are accelerated over distances of thousands of light years, allowing them to build up energies that are simply staggering. To truly grasp the scale of these energies, we use a unit called an electron volt. The protons that circulate in the Large Hadron Collider reach energies of about 13 trillion electron volts. This is an impressive number, but astrophysicists have detected cosmic rays with energies exceeding 100 million trillion electron volts. These are particles that carry the kinetic energy of a well-thrown baseball, all compressed into a single, minuscule proton. The forces required to achieve this are almost beyond comprehension, and supermassive black holes are one of the very few places in the universe with the raw power to serve as such an accelerator. When these ultra-high-energy cosmic rays finally collide with a molecule in our upper atmosphere, the resulting particle shower can span dozens of square kilometers, and the energy of the collision is so great that it allows scientists to study the fundamental properties of matter under conditions that have not existed since the first fleeting moments after the Big Bang. By building vast detector arrays on the ground, like the Pierre Auger Observatory, we can piece together the origin story of these mysterious travelers, using them as probes to test the limits of the standard model of particle physics and perhaps even discover entirely new phenomena. In this way, the most destructive objects in the universe are also our greatest allies in the quest to understand the very building blocks of reality. Given the staggering immensity of black holes like TON 618, a question naturally arises: is there a point where they simply cannot get any bigger? Is there a theoretical ceiling to their growth, a point where the universe itself says, enough? This fascinating question leads us to the complex and still evolving theories surrounding the ultimate size limit of these cosmic giants. The growth of a supermassive black hole is not an unchecked runaway process. It's a constant battle between feast and famine, governed by a fundamental balancing act known as the Eddington limit. Named after the astrophysicist Arthur Eddington, this principle states that there is a maximum rate at which a black hole can accrete matter. The reason is beautifully logical. As matter falls in and heats up, it emits intense radiation. This radiation exerts an outward pressure on the infalling material. At a certain luminosity, this radiation pressure becomes so powerful that it actually pushes away the surrounding gas and dust, effectively shutting off the black hole's own food supply. It's the cosmic equivalent of a fire becoming so hot that it blows its own fuel away. A black hole can exceed this limit for short, violent bursts, but sustained super-Eddington accretion is thought to be difficult. This physical break means that even the most voracious black hole can only consume matter so quickly, placing a fundamental constraint on how fast it can grow over time. Beyond this physical limit, a black hole's growth is ultimately constrained by its environment, specifically the sheer amount of mass available in its cosmic neighborhood. A black hole at the center of a galaxy can only consume the material that its gravity can draw in. Once it has devoured all the available gas and stars within its immediate reach, its growth severely slows down. It becomes dependent on new fuel sources, which primarily come from two places: galactic mergers and the rare, unfortunate star that wanders too close. As we've discussed, mergers with other galaxies can deliver a fresh supply of gas and even another black hole to consume. But the universe is expanding and galaxies are being pulled apart. In the far, far future, the amount of accessible matter within a black hole's gravitational grasp will diminish, effectively stranding these giants and halting their growth long before they could consume everything. So, what does the largest known black hole, TON 618, tell us about these theoretical limits? Its existence, especially at such an early cosmic epoch, is a significant puzzle. To reach 66 billion solar masses so quickly, it must have either grown at a super-Eddington rate for a sustained period defying the standard model, or it started from an unimaginably massive primordial seed, far larger than any we understand how to form. Its incredible size pushes at the very boundaries of our theories, suggesting that in the unique conditions of the early universe, with denser gas and more frequent interactions, the rules might have been different. TON 618 isn't just a record holder. It's a challenge, an outlier that forces us to refine our models of how the most extreme objects in the universe are born and grow. Therefore, while there is no absolute, hard-coded upper limit written into the laws of physics, there is a profound practical one. The maximum size a supermassive black hole can achieve is a function of time, the mass of its host galaxy's stellar bulge and dark matter halo, and its merger history. The largest black holes will be found at the hearts of the largest galaxies in the densest galaxy clusters, where the buffet of available matter was most plentiful. They represent the pinnacle of gravitational dominance within their local environment. They are not infinite, they are the ultimate products of their cosmic circumstances, having consumed a significant fraction of the mass that was once available to them, standing as final monuments to the awe-inspiring power of gravity over billions of years. This brings us to one of the most profound and mind-bending concepts in all of theoretical physics, an idea that suggests the universe might be a grand illusion, a cosmic projection. Fact 27 explores the radical possibility that black holes are not just objects in space, but that they might be teaching us that all of reality operates like a hologram. This is the holographic principle, a revolutionary idea proposing that the information needed to describe a three-dimensional volume of space, like everything inside a black hole's event horizon, might be entirely encoded on its two-dimensional boundary, much like the information for a 3D holographic image is stored on a 2D flat surface. The seed for this astonishing idea was planted by the black hole information paradox itself, as physicists grappled with the question of what happens to information that falls into a black hole. A startling calculation emerged. It was discovered that the maximum amount of information or entropy that a region of space can contain is not proportional to its volume, as common sense would dictate, but to the surface area of its boundary. For a black hole, this boundary is its event horizon. This was a profound clue that the true degrees of freedom, the fundamental bits of information that describe our reality, might actually reside on a distant, enclosing surface, and that the three-dimensional world we experience is a complex projection of that data. A black hole, with its clear boundary and terrifying ability to seemingly erase information, became the perfect laboratory for testing this idea. To grasp this, imagine the event horizon of a black hole not as a simple surface, but as a vast tapestry woven from unimaginably tiny, vibrating strings or quantum bits, each one Planck length in size. This tapestry contains all the information about everything that has ever fallen into the black hole. The three-dimensional interior we picture, with its swirling accretion disk and central singularity, is not the fundamental reality. It is a holographic projection, an emergent phenomenon generated from the complex interactions of that information on the two-dimensional surface. In this view, the black hole doesn't destroy information at all. It stores it scrambled and encrypted on its event horizon, and the Hawking radiation that slowly leaks out is not random but carries that encoded information back into the universe. The implications of this principle extend far beyond black holes, potentially rewriting our understanding of the entire cosmos. If the holographic principle holds true for a black hole, there is no reason it shouldn't apply to any volume of space. This suggests that the entire universe we inhabit, with its countless galaxies, stars, and planets, might itself be a holographic projection. All the information that defines your body, your memories, and everything you see around you could, in principle, be encoded on a vast, distant two-dimensional surface that surrounds us at the edge of the observable universe. We are not living in a fully three-dimensional reality, but are instead like characters in an immensely sophisticated video game whose entire code is written on a flat screen. This doesn't mean our experiences are not real, but that they are emergent properties of a deeper, more fundamental two-dimensional reality. The solidity of the world around us, the very nature of space and time, could be an illusion generated by quantum processes happening on a remote boundary we can never see. The holographic principle is perhaps the most radical clue we have that to truly understand the cosmos, we must look not inward but outward to the edges of existence itself. This complex dance of creation and destruction begins with the raw material of the universe, vast clouds of cold molecular gas. This is the stellar nursery, the cosmic hydrogen from which new stars are born when gravity causes dense patches to collapse. A supermassive black hole influences this process through two primary forms of feedback: negative feedback which suppresses star formation, and positive feedback which can surprisingly trigger it. The dominant force, especially in larger galaxies, is negative feedback. When a black hole enters an active phase, blazing as a quasar, the immense energy it releases doesn't just come from the glowing accretion disk. It also generates powerful, wide-angle winds that blast outward through the galaxy. These aren't the narrow jets, but broader, more diffuse outflows of energized particles and radiation. As these quasar winds slam into the cold gas clouds, they don't gently push them, they violently heat them. This heating is the crucial step. For a gas cloud to collapse and form stars, it needs to be cold and dense. By superheating this galactic fuel, the black hole's energy prevents it from cooling down and condensing, effectively putting a lid on the star-forming process. In more extreme cases, these winds are so powerful they can drive the gas right out of the galaxy entirely, ejecting the future building blocks of stars into the intergalactic medium and leaving the galaxy starved and unable to create new stellar generations. But the black hole's influence isn't always so destructive to star birth. Under the right conditions, it can also play the role of a cosmic midwife. This positive feedback often involves the colossal jets we discussed earlier. While these jets are incredibly narrow and focused, their impact as they plow through the galactic environment can be transformative. When the tip of a jet, moving at nearly the speed of light, rams into a massive, slow-moving cloud of cold gas on the outskirts of the galaxy, it doesn't always just blast it apart. The initial interaction creates a tremendous shock wave that propagates through the cloud. This shock wave acts like a giant cosmic snowplow, compressing the gas to unprecedented densities. Imagine a handful of fluffy snow being suddenly and violently packed into a dense, hard snowball. This sudden compression can be the catalyst that pushes a gas cloud over the critical threshold, causing it to fragment and collapse under its own gravity, igniting a burst of new star formation in a ring or shell around the jet's impact point. So, the same jet that can heat and disperse gas in one region can trigger a stellar baby boom in another, a stunning paradox that highlights the black hole's role as a complex regulator rather than a simple destroyer. This intricate feedback loop creates a fascinating self-regulation system for the entire galaxy. The black hole itself feeds on the surrounding gas, growing more massive. As it feeds, it becomes more active and begins to pour energy back into its environment. This energy then heats or ejects the very gas it needs to continue feeding, ultimately starving itself and halting its own growth. This elegant balance explains the remarkably tight correlation between the mass of a galaxy's central bulge and the mass of its supermassive black hole. They didn't just grow independently, they grew together, locked in a gravitational embrace where one directly controlled the growth of the other. The black hole acts as a cosmic thermostat, preventing the galaxy from becoming too large and ensuring a measured, stable evolution over billions of years. Without this regulatory mechanism, galaxies might consume their gas too quickly in a violent burst of star formation, burning out fast and leaving behind a lifeless husk. Instead, the silent, dark giant at the center ensures a long and structured life story for its galactic home, governing the rhythm of stellar birth and death from the shadows. But our quest to understand these cosmic giants is far from over. In fact, we stand on the precipice of a new golden age of discovery, powered by a suite of revolutionary instruments that will peer deeper into the darkness than ever before. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is already transforming our view of the early universe, allowing us to study the formation of the very first supermassive black holes and their host galaxies in unprecedented detail. By cutting through the cosmic dust that obscures these ancient objects, Webb is providing a crystal-clear window into an epoch when black holes and galaxies were just beginning their intricate dance of co-evolution, revealing how these gravitational anchors first took hold and began to shape the cosmos. While Webb observes the light from these distant behemoths, a different kind of observatory is preparing to listen to the very fabric of spacetime itself. The Laser Interferometer Space Antenna, or LISA, is a visionary mission that will open an entirely new window on the universe. Instead of relying on telescopes, LISA will consist of 3 spacecraft flying in a precise triangular formation millions of kilometers apart, connected by lasers. This gigantic instrument will detect the low-frequency gravitational waves generated by the mergers of supermassive black holes, events so massive and slow that they are undetectable from Earth. LISA will allow us to hear the cosmic symphony of these colossal collisions, mapping the population of black holes throughout the universe and witnessing the formation of the very largest giants through mergers that have never been directly observed. And for those who are captivated by the first blurry but magnificent image of a black hole's shadow, the future holds even greater clarity. The Event Horizon Telescope collaboration is not resting on its laurels. Plans are already underway to expand the array by adding new radio dishes across the globe and even launching space-based antennas. This next-generation EHT will achieve a resolution so sharp it could theoretically read the writing on a coin in New York from a cafe in Paris, but applied to the very edge of a black hole light years away. With this incredible power, we will no longer see a fuzzy ring of light. We will be able to make detailed movies of how matter flows and twists in the final moments before it crosses the event horizon, directly testing Einstein's predictions in extreme gravity, and perhaps even spotting the subtle signatures of a black hole's spin warping the spacetime around it. These technological marvels represent more than just incremental improvements. They are leapfrogging us into a new era of precision black hole astronomy. Together, they will transform these enigmatic objects from distant, mysterious monsters into detailed laboratories for fundamental physics, allowing us to witness their birth in the early universe, hear their mergers across cosmic time, and see their immediate environment with breathtaking clarity. The data they return will not just fill textbooks, it will challenge our most deeply held theories, potentially providing the first experimental evidence for quantum gravity, or revealing entirely new phenomena that we cannot yet even imagine. The next decade promises to peel back the veil on these dark giants, bringing us closer than ever to answering the profound questions they pose about the nature of space, time, and reality itself. But perhaps the most profound role for these cosmic giants is yet to come, one that connects the invisible anchor at the center of a galaxy to the ultimate fate of the entire cosmos. Our 30th and final fact ventures into the most speculative and revolutionary idea of all, that supermassive black holes might not just be inhabitants of the universe, they might be the very engine behind its accelerating expansion. This astonishing theory proposes a direct link between the growth of these gravitational behemoths and the mysterious force we call dark energy. For decades, one of the greatest puzzles in cosmology has been the discovery that the universe is not only expanding, but that this expansion is speeding up. Some unknown repulsive force, dubbed dark energy, appears to be counteracting gravity on the largest scales, pushing galaxies apart at an ever-increasing rate. The source of this energy has remained completely enigmatic, often attributed to a cosmological constant or a property of the vacuum of space itself. But a provocative new hypothesis suggests the answer might lie within the most gravitationally dominant objects we know. The idea centers on a concept known as vacuum energy. In quantum physics, empty space is not truly empty. It is a seething foam of virtual particles flickering in and out of existence, possessing our underlying energy density. If this vacuum energy is the source of dark energy, then a critical question arises: where is it stored, and how does it contribute to the cosmos's expansion? The revolutionary proposal is that the interior of a black hole, specifically the volume inside its event horizon, is the natural repository for this energy. As a black hole grows by consuming matter, its event horizon expands, and in doing so, it actually increases the total volume of space inside it that is filled with this repulsive vacuum energy. Think of it like this: the universe is a container holding two types of energy. Outside black holes, we have normal matter and energy that exert gravitational pull, trying to slow the expansion. But inside every black hole's event horizon, there is a volume of space that contains a repulsive form of energy. The larger the black hole grows, the more of this repulsive energy volume it contains. The math of general relativity suggests that this internal energy contributes to the overall energy budget of the universe in a way that drives accelerated expansion. In this view, the growth of cosmic structure, the very process of galaxies merging and their central black holes getting larger, is intrinsically linked to the acceleration of the universe itself. It's not a coincidence that the acceleration began a few billion years ago. That was the epoch when the universe had expanded and cooled enough for large-scale structure to form, and for supermassive black holes to become prevalent and begin their most significant growth phases. This theory, while still highly speculative and debated, offers a stunningly elegant connection between the very largest and smallest scales of physics. It posits that the same quantum vacuum energy that pervades all of space becomes cosmologically significant when it is sequestered inside the event horizons of black holes. The more massive the black hole, the greater its interior volume, and the more it contributes to the dark energy driving the universe apart. This would mean that the dark energy problem isn't a question of some exotic new field, but rather a question of understanding the thermodynamics and quantum properties of spacetime inside black holes. It transforms these objects from passive consumers of matter into active participants in shaping the cosmic destiny, their growth directly feeding the force that will ultimately determine the fate of everything. While this idea needs much more theoretical development and observational testing, it represents a breathtaking synthesis of ideas, suggesting that the key to understanding the universe's expansion has been hiding in plain sight at the heart of every galaxy all along. And so our journey across the cosmos brings us face to face with the profound legacy of these gravitational titans. We've ventured from the supermassive anchor at the heart of our own galaxy to the incomprehensible scale of Ton 618, a colossus holding 66 billion suns within its dark embrace. We've witnessed how their immense spin drags the very fabric of spacetime into a whirlpool, explored the brilliant quasars they power that outshine entire galaxies, and grappled with the quantum paradoxes they create at their boundaries. These are not the simple vacuum cleaners of science fiction, but the universe's ultimate architects and regulators, governing the birth of stars, the growth of galaxies, and perhaps even the fate of the cosmos itself through their mysterious connection to dark energy. The most mind-bending realization is how these cosmic giants consistently dismantle our assumptions and force us to rewrite the textbooks of physics. They are natural laboratories where the known laws of reality break down, where time stretches to a standstill and space becomes a tangled knot. The existence of billion solar, mass black holes in the infant universe challenges our models of cosmic growth, while the fiery information paradox pits Einstein's general relativity against quantum mechanics in a fundamental conflict that may only be resolved by a theory of everything. Each discovery, from the first image of a black hole's shadow to the faint chirp of gravitational waves, doesn't just provide answers. It opens deeper, more fascinating questions about the nature of existence. This endless cycle of mystery and revelation is what makes the study of our universe so thrilling. Just when we think we understand the rules, a black hole reveals another layer of complexity, reminding us that curiosity is our most powerful tool for exploration. The future of discovery has never been brighter, with revolutionary tools like the James Webb Space Telescope peering back to the dawn of time, and the Laser Interferometer Space Antenna preparing to listen to the mergers of supermassive giants. If you've found this voyage as captivating as we have, and you want to join us as we continue to unravel the deepest secrets of the cosmos, Make sure to subscribe and hit the bell for more content. Our next adventure is always just beyond the event horizon, waiting to reveal wonders beyond our wildest imagination.